I have pleasure. Oh, very good and very in time said. So I have a pleasure to announce the talk of my co-organizer, Dr. Pirkovskii. No, well, and so please, Alexei Yulievich, please begin.
Thank you. So the subject of my talk is closely related to what I was talking about here in May. But I'd like to stress that today's talk will be totally independent of the previous one. I'm going to tell you about flat topological modules and a new Tor functor. And let me start with some history and some motivation. In the purely algebraic setting, flat modules over rings were introduced in 1956 by Jean-Pierre Serre in his famous paper on relation between algebraic and complex analytic geometry. And the same year, the notion of a flat module appeared in the famous book by Cartan and Eilenberg, Logical Algebra. Flat modules are quite important objects, for example, in ring theory and in algebraic geometry. In the context of functional analysis, flat Banach modules over Banach algebras were introduced by Alexander Yakovlevich Chelemsky in 1972 and were extensively studied in the 1970s by Chelemsky and Schoenberg. Flat Banach modules are important for many reasons, but especially because they are closely related to amenable Banach algebras. Some results on flat Banach modules were extended in my paper of 2006 to flat Fréchet modules over flat Fréchet algebras. Anyway, in all these cases, I mean, in the pure algebraic case, and in the setting of Banach modules, and in the setting of Fréchet modules, in all these cases, the property of flatness can be characterized in terms of the derived functor Tor. Unfortunately, almost nothing is known about flat modules in the context of more general, that is, non-metrizable locally convex modules. Recently, in our joint paper with Krzysztof Piszczyk from Adam Mickiewicz University in Poznań, we observed that the traditional definition of flatness, which is canonical in the case of Banach modules and in the case of Fréchet modules, this definition is irrelevant, is not very convenient in the non-metrizable setting. And we suggested a modified definition, which works better in many concrete situations. However, a problem with the new definition is that flat locally convex modules cannot be characterized in terms of the Tor functor. So a solution, or maybe a quasi-solution of this problem, which I'm going to tell you about today, is to redefine the Tor functor, that is to consider another version of the Tor functor, which will enable us in particular to characterize flat modules. And I hope that this new version of the Tor functor can be helpful in some other situations. Okay. Please forgive me my handwritten notes. So first of all, a little convention. So everything will be over the complex numbers. So all vector spaces and all algebras will be over the complex numbers. Algebras are assumed to be associative, but not necessarily unital. So let's specify the class of topological algebras we are going to consider. So all our topological algebras are assumed to be complete, locally convex, and having jointly continuous multiplication. Such algebras are often called algebras relative to the projective tensor product. because the multiplication in such an algebra uniquely factorizes through the completed projective tensor product. So this explains the name for such algebras. Unfortunately, this name, which is shown here in red, I mean algebra relative to the projective tensor product, is very difficult to pronounce. So if you don't mind, I'll call them just topological algebras. So I call them just topological algebras, but I always mean that they are complete and have jointly continuous multiplication. As usual, a Fréchet algebra is a metrizable topological algebra, that is a complete metrizable topological algebra over the complex numbers. Here are some examples of topological algebras. First of all, it's clear that Banach algebras are topological algebras in our sense. Next, if X is a topological space, which is not very bad, then C of X, the algebra of continuous functions on X, equipped with the compact open topology, is a topological algebra. So if X is very bad, then it is not complete. But if X is nice enough, then it is complete. So it is a topological algebra in our sense. And in particular, if X is locally compact and sigma compact, then C of X is a Fréchet algebra. Next, the algebra of smooth functions, C infinity of M, the algebra of smooth functions on a smooth real manifold, the algebra of holomorphic functions on a complex analytic manifold, and the Schwarz algebra over Rn, all of them are Fréchet algebras. And the standard examples of non-metrizable topological algebras are the algebra of compactly supported distributions on a real Lie group, and the algebra of analytic functionals on a complex Lie group, which is, well, the underlying space of this algebra is just the strong dual of the space of holomorphic functions. And the multiplication is convolution. So they are non-metrizable topological algebras. Now, if we have a topological algebra in our sense, then a left topological A module, or more exactly, a left topological A module relative to the projective tensor product, is a left A module together with a complete locally convex topology, such that the action of A on this module is jointly continuous. Well, clearly all left topological A modules form a category. So morphisms here are just continuous A module homomorphisms. And similarly, we can consider the category of right topological A modules and the category of topological A bimodules. Now, if the underlying locally convex space of our algebra has some nice linear topological properties, then it is natural to consider only those topological modules whose underlying spaces have the same linear topological property. And formally, this can be achieved as follows. So first we consider the category of all complete locally convex spaces. And suppose that we have a full additive subcategory in this category. And we say that this subcategory is admissible if it is stable under completed projective tensor products and under topological direct summands. Mm-hmm. In fact, most standard categories which are used in functional analysis are admissible. For example, we can consider the category of Banach spaces, the category of Fréchet spaces, of course, the whole category of complete locally convex spaces, the category of complete DF spaces, or the category of complete nuclear spaces, and of course, there are many other natural examples. So all these categories are admissible. But there are also counterexamples. For example, if you take the category of complete barreled spaces, it is not admissible because it is known that the projective tensor product of two barreled spaces is not necessarily barreled. Mm. Okay, so now if C is an admissible, subcategory of complete locally convex spaces, and if we have an algebra A a topological algebra whose underlying locally convex space belongs to C, and in this case we write we use such a notation. So alg of C is the category of all topological algebras whose underlying spaces belong to C. So in this case, we can consider the full subcategory in the category of all topological A modules, such that the underlying spaces of our modules belong to C. So this is the category where we want to develop homological algebra. Well, actually, homological algebra in such categories were first introduced and developed by Alexei Pirkovskii in 1970, in a special case where A is a Banach algebra and C is the category of Banach spaces. And shortly afterwards, a similar theory was created by Killian and Verdier in 1971 and by Joseph Taylor in 1972 in the more general context of locally convex modules. Roughly, the main difference, the main technical difference between this kind of homological algebra and the classical homological algebra by Cartan and Ehrenberg is that in the functional analytic setting, we must replace exact sequences, not everywhere, but in suitable places. We must replace exact sequences by the so-called admissible sequences. So by definition, a short sequence of this form in the category of topological modules is called admissible if it is split exact in the category of locally convex spaces. That is, if it has a contracting homotopy consisting of continuous linear maps. If we say this, if we rephrase this in more analytic or topological terms, this means that the first map I is topological injective, that it is a topological embedding. P is open. P is an open map of I of Y onto Z. And well, also we have algebraic exactness in the middle term. That is the range of I is the kernel of P. And finally, I of X should be a complemented subspace of Y. So this means that our sequence is admissible. The first arrow in this diagram, I, is called an admissible monomorphism, and P is an admissible epimorphism. Well, we can now define projective modules in our category. So a topological module P is projective if the functor of morphisms, the home functor, where P is fixed in the first variable. So we consider home as a functor of the second variable. And we consider this functor as a functor from the category of left topological A modules to the category of vector spaces. And we say that P is projective if this functor is exact, in the sense that it takes admissible sequences of topological modules to exact sequences of vector spaces. And the fundamental fact is that the category of topological A modules has enough projectives, which means that for each topological A module X, there is a projective topological A module P and an admissible epimorphism of P onto X. And this fact implies that each topological A module X has projective resolution. So what is a projective resolution? It is a chain complex P concentrated in non-negative degrees, such that all modules in this complex are projective, together with a morphism epsilon from P0 to X, such that the resulting augmented complex, which is shown here, is admissible. Well, formally, I have just defined admissible sequences only in the case of short sequences, but for chain complexes, the definition is the same. We say that it is admissible if it is split exact in the category of locally convex spaces. That is,
I'm sorry, the module P is not from the same category, right? Or it should be.
No, all of them are, sorry, I didn't write this explicitly, but of course I mean that all of them belong to the same category.
I see, okay, thanks.
Okay. Okay, we can now define by using projective resolutions, we can now define the derived functors x and tor. So suppose that x and y are two left topological A modules. Then we take any projective resolution P of x. We consider the co-chain complex of morphisms from P to Y. And for each n, we take the nth cohomology. And the space is denoted by xn. And actually, it is the nth derived functor of the home functor. Now, if x is a right topological A module and y is a left topological A module, we can define the derived functor tor as follows. Again, we replace x with a projective resolution P of x. We form the tensor product complex, the tensor product of P and Y, or more exactly, the completed projective tensor product of P and Y over A, and we take the nth homology of this complex. Or equivalently, we can solve this, and in fact, this construction is symmetric. So alternatively, we can take a projective resolution of Y, replace Y by this resolution, tensor by X, and then take the nth homology. And this gives us the same tor space. Okay. Here are some basic facts on X and tor. First of all, exactly as in the classical homological algebra of Cartan and Ehrenberg, the functor x0 is just the home functor. And also, again, exactly as in the classical homological algebra, we have the following characterization of projectivity in terms of x functors. So P is projective, even only if the functor x1, where P sits in the first argument, vanishes. And this is equivalent to say that xn vanishes if n is greater than or equal to 1. The next fact is, it could be a little surprise for those of you who are familiar with classical homological algebra, but probably not familiar with Banach homological algebra. Of course, if there are some people here who are not familiar with Banach homological algebra. So the surprise is that the functor tor0 is not the same as the tensor product. So in the classical homological algebra, these functors are isomorphic, but not here. The reason is that, in contrast to the pure algebraic tensor product, the completed projective tensor product is not right exact when we consider it as a functor from right topological A modules to the category of vector spaces. This means that if we have an admissible sequence of right topological A modules, tensor it by an arbitrary module y, and remove 0 from the left, so we consider this sequence. This sequence of vector spaces is not necessarily exact. So this means that our functor is not right exact, and this is the main reason why tor0 is different from the tensor product. Nevertheless, there is a nice relation between the tensor product and the tor0. Actually, the tensor product is the completion of tor0. Or more exactly, since tor0 is not necessarily Hausdorff, we must first take the we must quotient out the closure of 0. That is, we first of all form the associated Hausdorff locally convex space, and then we take the completion. By the way, if we work with Fréchet modules, then this quotient is already complete and is isomorphic to the projective tensor product. Okay, now to define flat modules, first of all, I give the classical definition. And let's suppose that C, our base category of locally convex spaces, is either the category of Banach spaces or more generally the category of Fréchet spaces. We say that left A module F is flat if the tensor product by F, which acts from the functor acts from the category of right A modules to the category of vector spaces, is exact in the same sense that it takes admissible sequences of right topological A modules to exact sequences of vector spaces.
Oh.
Well, when we look at this definition, we may ask, well, why do we require that C is the category of Banach spaces or the category of Fréchet spaces? It seems natural to give the same definition, exactly the same definition, in the more general context of an arbitrary admissible subcategory C. Unfortunately, there will be some problems with such a definition. If we adopt the same definition for a more general categories C, then we quickly encounter many problems. I explained such problems in detail at my previous talk, so today I'll just very briefly mention some of them. First of all, it turns out that if we adopt such a definition for more general topological modules, then we can prove almost nothing interesting about flat modules. And the reason is that if we try to analyze the proofs of some non-trivial results about flat Banach modules, it turns out that the assumption of normability is very essential for the proofs. And the same happens with Fréchet modules. So we cannot just remove the assumption of metrizability. So this destroys almost all the proofs. So this is the first reason why this definition is not useful in the non-metrizable context. And moreover, it turns out that we can meet some pathologies in the non-metrizable case. For example, if we adopt the same definition, again, if we adopt the same definition of flatness in the non-metrizable context, then it turns out that there exist non-flat topological modules over the algebra C0 of omega, where omega is a locally compact Hausdorff topological space.
Despite amenability, yes? Despite
amenability. So why this, in fact, actually, why is this a pathology? So let me recall that C0 of omega is amenable in the sense of Johnson. And as was observed by Alexander Yakrich and Schoenberg, all Banach modules over an amenable Banach algebra are flat. And in fact, the same is true for Fréchet modules over an amenable Fréchet algebra. And so we see that if we take the same definition of flatness in the non-metrizable context, then there exist non-flat modules over this algebra, which of course looks like a pathology. So all this shows that the definition of a flat topological module should be modified. And before I call the modified definition, let me define strictly exact. Let me define the notion of a strictly exact sequence. So suppose that we have an arbitrary additive category A, and suppose that we have a short sequence of this form in our category. This sequence is called the strictly exact, or a kernel-co-kernel pair, if f, the first arrow in the sequence, is the kernel of G, and G is a co-kernel of F. Well, let's look at some examples. First of all, if A is an abelian category, for example, you may think about the category of modules over a ring, then a sequence is strictly exact if and only if it is exact. On the other hand, if you now take the category of complete locally convex spaces, and probably this is our main example, then the situation is different. It turns out that such a sequence is strictly exact if the following conditions hold. First of all, F is topologically injective. Second, our sequence should be algebraically exact in the middle term. That is, the range of F is equal to the kernel of G. Next, the second arrow G must have a dense range. So the range of G is dense in Z. And finally, G should be an open map of Y onto G of Y, onto its range. So if we look at these conditions more carefully, it turns out that this is essentially equivalent to the assumption that X is that F is a topological embedding of X into Y. So X can be identified with a closed subspace of Y. and Z is nothing but the completion of the quotient of Y modulo X. So I'd like to stress that in the non-trivial case, we must take the completion, because the quotient of a complete space, modulo a closed subspace, is not necessarily complete. And finally, if A is the category of Banach spaces, or the category of Fréchet spaces, then it turns out that a sequence in this category is strictly exact, if and only if it is strictly exact in the category of all complete locally convex spaces. And this happens if and only if it is exact in the category of vector spaces. This is a simple exercise in functional analysis. In fact, if it is exact in the category of vector spaces, then the open mapping theorem implies that, F is topologically injective, because it is injective and its range is closed. And the range is closed because this is equal to the kernel of G. So F is a topological embedding, and G is open because it is surjective. And the other way around, if we have if our sequence is strictly exact in the category of complete locally convex spaces, so we look here and we see that there is no need to take the completion of the quotient, because the quotient of a Fréchet space modulo a closed subspace is already complete, and we get the exactness in the category of vector spaces. Okay, we can now introduce flat topological modules. So suppose that C is an admissible subcategory in the category of complete locally convex spaces, and A is a topological algebra whose underlying topological vector space belongs to C. And suppose that F is a left topological A module in the respective category, A mode of C. And we say that F is flat if the projective tensor product functor by F. And now we consider this functor as a functor to the category of complete locally convex spaces. And we say that F is flat if this functor takes admissible sequences of topological modules to strictly exact sequences of complete locally convex spaces. If C is the category of Banach spaces or the category of Fréchet spaces, we see that this definition is equivalent to our earlier definition, that is the classical definition of flatness, just because of this remark. So strict exactness in this category is equivalent to algebraic exactness, to the exactness in the category of vector spaces. Let me briefly explain. Again, the details were given at my previous talk, but nevertheless, let me briefly explain some advantages of this new definition of flatness. The first advantage, which is not on my slide, is that this definition is compatible with amenability. So such pathologies, as shown here, are impossible, are no longer possible. So if you have an amenable Banach algebra, or an amenable Fréchet algebra, or an amenable topological algebra, then all topological modules over such an algebra will be flat. Another nice property of this definition is that by using this definition of flatness, we can characterize amenability for complete barreled DF algebras. This was done in our joint paper with Pirkovskii. So actually, this is an extension of Hellemsky and Chambers' criterion to complete barreled DF algebras. So if A is such an algebra and C is the category of complete barreled DF spaces, then it turns out that the unitization of A plus, is a flat topological A bimodule, if and only if the first continuous Hochschild cohomology of A with coefficients in any dual topological bimodule, I mean dual to X, where X runs over this category, vanishes. That is, all derivations from A to X star are inner. By using this criterion, it's possible to give a convenient characterization of amenability for the so-called chaotic co-echelon algebras. This was also done in our joint paper with Krzysztof Piszczek. Another advantage of this definition is that if we define flat modules in this way, then we can extend another useful result by Helmsky and Scheinberg, namely the flatness criterion for a cyclic module. It turns out that this criterion can be generalized to topological modules over an arbitrary Arith-Michael algebra. So these are the main advantages. On the other hand, the new definition of flatness has a little disadvantage, or maybe not so little. It turns out that flat topological modules, in general, cannot be characterized in terms of the derived functor Tor. By the way, I see now that I forgot to include here a characterization of flatness in terms of the Tor functor for Banach modules and for Fréchet modules. So let me add it now. Fortunately, I have a little space here. So let me recall the following result. Again, at this point, we assume that C is either the category of Banach spaces or the category of Fréchet spaces. Then F is flat, if and only if for each right A module X, right topological A module X, the functor Tor1 vanishes. Tor1 of XF is 0. And the functor Tor0, the Tor0 space, is Hausdorff. So this is one of the classical results about flat Banach modules due to Alexander Pirkovskii. By the way, it is similar to the well-known characterization of flat modules in the pure algebraic context. So in the pure algebraic context, a module F over an arbitrary ring is flat, even only if Tor1 vanishes. But in the context of Banach modules and in the context of Fréchet modules, we must also require that Tor0 is Hausdorff. Okay, so this is a very useful characterization of flat Banach modules in terms of the functor Tor. And it turns out that such a characterization is not available in the context of non-metrizable topological module. And this is the main disadvantage of our new definition. The main reason for this phenomenon is that a strictly exact sequence of complete locally convex spaces is not necessarily exact in the category of vector spaces. And the other way around, if our sequence is exact in the category of vector spaces, it is not necessarily strictly exact in the category of complete locally convex spaces. So there are no such implications. A solution, or maybe a quasi-solution to this problem, is to redefine the functor Tor. And this is exactly what I'm going to do now. But before we can redefine the functor Tor, I must recall some basic facts about derived categories and derived functors, because these tools are absolutely necessary for the new definition of the Tor functor. Derived categories and derived functors are traditionally defined in the context of abelian categories, but this context is not general enough for our purposes. And probably the most convenient setting for our purposes is the setting of right exact categories. By definition, a right exact category is a pair consisting of an additive category A and a subclass K, subclass of the class of all kernels in A. which satisfies the following axioms. First, the identity morphism of the zero object should belong to this class. Second, this class must be stable under composition. So the composition of two kernels belonging to EK belongs to the same class. And finally, this class should be stable under push-outs, in the sense that if you have a push-out diagram here, in which I belongs to our specified class of kernels, then I prime also belongs to the same class. Well, just in case, let me briefly recall what a push-out diagram is. This is a purely category theoretic notion. So if you have an arbitrary category and two morphisms, F from X to Y and G from X to Z, so two morphisms with the same domain, we can consider the category of all diagrams of this form. So here X, Y, Z, F, and G are fixed, and W and these two errors are arbitrary. So it's more or less clear how to define morphisms in the category of all such diagrams. And by definition, the push-out of F and G is the initial object in this category. And normally it is denoted like this. So in most concrete cases, this object is constructed as a suitable quotient of the co-product of Y and Z. So this explains the notation. Okay, so suppose now we have a right exact category. So in this case, the morphisms belonging to our class of kernels are called admissible monomorphisms, or inflations in other terminology. And let's now consider the class of co-kernels of admissible monomorphisms. So the co-kernels of admissible monomorphisms are called admissible epimorphisms or deflations. And finally, if you have a short strictly exact sequence in our category, I will say that the sequence is admissible or is a conflation if the first arrow I here is an admissible monomorphism, or equivalently if the second arrow P is an admissible epimorphism. And the class of all short admissible sequences will be denoted by script E. So if we look at this definition, we see that the class EK, the class EC, and the class E are, well, each of them determines, so they determine each other, in the sense that once we have EK, we may define EC, the class of co-kernels of morphisms in EK, and this gives us E. But we can do the opposite procedure. We may start with E, and E determines EK, both EK and EC. Okay, so this is the definition of a right exact category. Left exact categories are defined dually. We start with EC. We define axiomatically the class of admissible epimorphisms. And in particular, we require that the pullback of an admissible epimorphism should be an admissible epimorphism. And finally, we say that A, together with a distinguished class of short sequences, is an exact category if it is both right exact and left exact. An important special case of this notion is the notion of quasi-abelian and the one-sided quasi-abelian categories. So suppose that A is an additive category with kernels and co-kernels. So we assume that each morphism has a kernel and a co-kernel. And we say that A is right quasi-abelian if A, together with the class of all kernels in A, so this pair is a right exact category. So in this case, we say that A is right quasi-abelian. And similarly, we can define left quasi-abelian categories and quasi-abelian categories. Here's some history of this notion. The notion of an exact category is usually attributed to Quillen, or more exactly to his paper on higher algebraic K-theory, published in 1973. But at the same time, actually not equivalent, but a very closely related notion was introduced by Heller almost, well, more than a decade before Quillen. Quasi-abelian categories were introduced by Rykov in 1969 under a different name, so he called them semi-abelian categories. And in 1999, they were introduced independently by Schneiders and also by Rump in 2001. One-sided exact categories, that is left exact and right exact categories, explicitly appeared in a paper by Bazzoni and Krivy of 2013. And in a special case, left and right quasi-abelian categories were introduced again by Rump in 2001. Well, here are some examples of quasi-abelian, one-sided quasi-abelian, and exact categories. First of all, many classical categories of functional analysis are quasi-abelian. The category of Banach spaces, the category of Fréchet spaces, the category of all locally convex spaces, and the category of all Hausdorff locally convex spaces are quasi-abelian. On the other hand, the category of all complete locally convex spaces is right quasi-abelian, but it is not quasi-abelian. This was observed by Fabien Prosman in 2000. And this is the main reason why I've just defined right quasi-abelian categories, just because we have this classical example of a category which is not quasi-abelian, so it is not an exact category. And another important example is as follows. Suppose that script C is an admissible subcategory of complete locally convex spaces, and A is an algebra whose underlying space belongs to C. And let's consider the respective category of topological A modules. So we define admissible monomorphisms to be those morphisms in our category which are co-retractions in the category of complete locally convex spaces. So similarly, admissible epimorphisms will be those morphisms which are retractions of complete locally convex spaces. And as a result, the class of admissible sequences consists of those sequences which are split exact in the category of complete locally convex spaces. In other words, these are exactly admissible sequences in the sense of Helmsky. And it's rather easy to show that if we define the exact structure in this way, then indeed we get an exact category. So the category of topological A modules is an exact category. Okay, now let's briefly discuss the construction of the derived category in the context of right exact categories. So basically, the construction consists of 3 steps. We start with the right exact category A. And at the first step, we form the category COA of co-chain complexes over A. To work with chain and co-chain complex simultaneously, we adopt the following standard convention. So if we have a chain complex over our category A, we always make it into co-chain complex by the following rule. So this simple trick enables us to work with co-chain complexes only. So the next step is as follows. We take the category of co-chain complexes and we quotient out the 0 homotopic maps. And we come to the so-called homotopic category, which for some strange reason is traditionally denoted by KOA. I don't know why. In my view, HOA will be more logical, but anyway, KOA is the standard notation. So, so the objects of this category are still co-chain complexes, and the morphisms are morphisms of co-chain complexes modulo 0 homotopic maps. And the final step in our construction is so-called localization. Roughly, we take the homotopic category and we add new morphisms to this category. So the goal is to make all quasi-isomorphisms invertible. And so the morphisms in the new category, so the objects are still, the objects of the derived category are still co-chain complexes. And the morphisms can be thought of as fractions, or more exactly right fractions of this form, where F is an arbitrary morphism and S is a quasi-isomorphism. Well, let me now explain this in a little bit more detail. So I must explain what a quasi-isomorphism is and what I mean by a right fraction. Roughly, this is the procedure of constructing the derived category out of the homotopic category. This process of localization is very similar to localization in ring theory. So the typical example to keep in mind is the construction of rational numbers out of the integers. Okay, so what is a quasi-isomorphism? First of all, if we have a co-chain complex over A, we say that it is admissible if each differential in this complex has a kernel, and the following short sequence, just shown here, is admissible. That is, it belongs to our exact, more exactly right exact structure. Here are some special cases. If A is an abelian category, then it's rather easy to show that a co-chain complex is admissible even only if it is exact. On the other hand, if we take the category of topological A modules, then a co-chain complex in this category is admissible, even only if it is contractible, that is, split exact in the category of complete locally convex spaces. That is, if it has a contracting homotopy consisting of continuous linear operators. Now, if we have a morphism, an arbitrary morphism F in the category of co-chain complex, we define the cone of this morphism as follows. So this is the nth term of this cone complex, and the differential in this complex is given by the following 2x2 matrix. Also, if X is a co-chain complex, we can define the shift of X, denoted by X of 1, as follows. So we simply would take X and shift it to the left by 1 degree. And we also change the sign of the differential. Now, once we have a morphism F from X to Y, we can construct a sequence of the following form, which is quite natural. So alpha is just the obvious inclusion of Y into the cone onto the second summand, and beta is just the projection of the cone onto the first summand, which is the shifted complex X. And obviously, this sequence splits at each degree. By definition, a morphism F is a quasi-isomorphism if its cone is admissible. And here are two special cases. If our category is abelian, then it's rather easy to show that F is a quasi-isomorphism, even only if it induces an isomorphism in cohomology. And this easily follows from the above sequence. So if we look at this short exact sequence of co-chain complex, and if you write the long exact cohomology sequence, we see that the cone is exact, even only if the connecting maps from the cohomology of this complex to the cohomology of this complex are all isomorphisms. But these connecting maps are nothing but the maps induced by F in cohomology. So this is the Abelian case. And if we take now the category of topological A modules, then the situation is different. It turns out that F, morphism F of co-chain complexes of topological modules is a quasi-isomorphism, if and only if it is a homotopy equivalence over the category of complete locally convex spaces. The rigorous definition of morphisms in the derived category looks as follows. So we consider all diagrams of this form, where S is a quasi-isomorphism and F is an arbitrary morphism from Z to Y, and we define an equivalence relation on such diagrams. So two such diagrams are equivalent if they fit into such picture. This is so I omit the details, but this is very similar to the construction of rings of localization in ring theory. So this is the derived category. Now let's observe that the initial category A embeds as a full subcategory of the derived category as follows. So we can identify each object of A with the co-chain complex concentrated in degree 0. And this is a full embedding of A into the derived category. Okay, let's now discuss derived functors between derived categories. So suppose that we have two right exact categories A and B, and an additive covariant functor F from A to B. So clearly this functor induces a functor between the categories of co-chain complexes. We just apply F component-wise to the co-chain complexes. And this functor takes 0 homotopic maps to 0 homotopic maps. So it gives us a respective functor between the homotopic categories. And let's now look at the following picture. So we have the functor K of F, and we have two natural functors from the homotopic categories to the derived categories. And by looking at this picture, it's natural to ask, can we find a functor between the derived categories, D of F, which makes the diagram commute? Fortunately, in general, the answer is no. So why do I say fortunately? Because if such a functor D of F existed always, then there would be no homological algebra at all. And there would be no cohomology theory. Such a functor exists even only if F is exact. So by definition, our functor F is exact if it takes admissible sequences to admissible sequences, or equivalently, if it takes quasi-isomorphisms to quasi-isomorphisms. It turns out that there is a functor D of F which makes this diagram commute if and only if F is exact. So now a rough idea of a derived functor is as follows. So if F is not exact, then we can try to construct some kind of approximation to this non-existing arrow, and such an approximation will be a left exact functor of F. This is just a rough idea. Let me now explain some details. I'll not give you the most general definition of a derived functor. Maybe it is convenient, but it requires the general definition of a derived functor requires some preliminaries, and probably it is not easy to understand at the first glance. So instead of that, I'll give you a constructive definition, which is sufficient for our purposes. So the key assumption we make here is that our category A has enough projectives. Projective objects. So far I didn't define projective objects, but the definition of a projective object in an arbitrary right exact category is exactly the same as in the category of topological A modules. So the home functor, where our object is in the first argument, should be exact. So it should take admissible sequences to exact sequences of of billion groups. Okay, so we assume that A has enough projectives. We denote by P the full subcategory of A consisting of projective objects. Also, for technical reasons, we will consider not arbitrary co-chain complex, but only those complexes which are right-bounded in this sense. So we denote by C minus of A the category of those co-chain complexes which satisfy this condition. So Xn should be 0 if n is big enough. And similarly, we consider the homotopy category of right-bounded complexes and the right-bounded derived category, D minus of A. A standard fact is that once we have enough projectives, it turns out that every right-bounded co-chain complex has a projective resolution, or the so-called Cartan-Lindemp resolution. So what is this? This is a right-bounded co-chain complex P consisting of projective objects together with a quasi-isomorphism from P to X. So in the special case where X is an object of A, well, not an arbitrary complex, but just an object of A, we get the traditional definition of projective resolution. Okay, now we can define the derived functor of f as follows. So we look at the following picture. So we have k minus of f, which acts between the respective homotopy categories. We have a natural functor from k minus of p to k minus of a, where p is the subcategory of projectives. And it's rather easy to see that if we compose these two arrows, that is, if we restrict k minus of f to the subcategory corresponding to projective, then we get an exact functor from here to here. And since it's exact, it induces a functor between the derived categories from d minus of p to d minus of b. So we get this. But on the other hand, since P consists of projectives, it can be shown that the canonical inclusion of d minus of P into d minus of A is actually an equivalence of categories. So now we can define the left-derived functor of f as follows. First, we go from here to here, and then we apply alpha. So the left-derived functor of f is given by the following position. And it acts from d minus of A to d minus of B. And it is called the left-derived functor, or more exactly, the total left-derived functor. So here the word total emphasizes the fact that this functor acts between the derived categories. It's quite easy to describe the action of this functor on objects. Namely, if X is an object of the derived category, that is a right-bounded co-chain complex, we simply replace X by a projective resolution and apply f component-wise. That's it. In a special case where the category B is quasi-abelian, we can also define the so-called classical left-derived functors of f as follows. First of all, we have the so-called cohomology functors from the category of co-chain complexes of B to B itself. So in the abelian case, the cohomology functors are well known. And for an arbitrary quasi-abelian category, it was observed by Kopolov and Kuzminov in 2003 that the two possible candidates for the cohomology functors are actually equivalent. And so the cohomology functors are well defined. And moreover, every such functors factors through the derived category. And so we obtain cohomology functors from the derived category d of b to b. And now we define for each integer n, we define the nth classical left-derived functor of f as follows. We take the total left-derived functor of f, we restrict it to a, so we get a functor from a to d of b, and then we compose it with the minus nth cohomology functor on d of b. And as a result, we get a functor from a to b. This is the nth classical left-derived functor of f. And here is a typical example, which is important for our purposes. Suppose that A is the category of topological A modules, and B is the category of all, that is not necessarily complete, but not necessarily Hausdorff, the category of all locally convex spaces. Then for each right topological A module X, we can consider the tensor product functor f, which acts from A to B. So since the category of right topological A models has enough projectives, we can form the total left-derived functor. And since B is quasi-abelian, we can consider the nth classical left-derived functor. And it's immediate from the definition that this functor is nothing but the Tor functor, which was defined at the beginning of my talk. In fact, if we look again at the total derived functor of the tensor product, it can be shown, it's more or less standard fact of homological algebra, that this functor extends to a bifunctor defined on the product of the respective derived categories of right topological modules and left topological modules, and it takes values in the derived category of locally convex spaces. Okay, now before I define the new Tor functor, let's briefly recall some facts, some definition related to T structures and their hearts. The notion of a T structure was introduced by Belin-Sonderstein and Deligne in 1982. And roughly, a T structure is a tool for finding a billion subcategories of the derived category of A. I'd like to stress that here A is again an arbitrary right exact category. A itself is not necessarily a billion. So before we define T structures, let me explain what a distinguished triangle is. So we start with the right exact category A, and we define a triangle in the homotopic category or in the derived category of A to be any diagram of the following form. So here F and G are arbitrary morphisms. F acts from X to Y and G acts from Y to Z. And the final arrow acts from Z to the shifted X. Well, morphisms between triangles are defined in an obvious way. So a morphism from the first triangle to the second one is just a triple of morphisms U, V, and W, making this diagram commute. And here's an important example of a triangle. Suppose we have a morphism F in the homotopic category. Then each such morphism fits into the following triangle. So I have already defined the inclusion of Y into the cone of F and the projection of the cone onto the shifted X. So if we add the X to the left of this diagram, we get a triangle in the homotopic category. And by definition, a distinguished triangle in the homotopic category is a triangle isomorphic to a triangle of this form. If now look at the derived category, we define a distinguished triangle in the derived category to be the image of any distinguished triangle in the homotopic category under the canonical functor from KOA to DOA. So as a result, we see that both the homotopic category and the derived category are equipped with an X structure, the so-called structure of a triangulated category. So a triangulated category is an additive category in which distinguished triangles are defined axiomatically. But in this talk, we will not need the general definition of a triangulated category. We will work only with homotopic categories and derived categories. And now, before I define T structures, let's look at the basic example of a T structure. So this basic example is actually a motivation to introduce genealogy structures axiomatically. So suppose that A is an abelian category. So this assumption is essential here. And let's form the derived category of A. And for each integer k, we consider the following two full subcategories of the derived category. So the first full subcategory consists of those co-chain complexes whose cohomology vanishes in degrees greater than k. And similarly, the second subcategory consists of those complexes whose cohomology vanishes in degrees less than k. So in some sense, the objects of the complexes from the first subcategory are those which are cohomologically concentrated in degrees less than or equal to k. So this explains the notation. We have, as a result, we have two chains of full subcategories of D. The first chain is increasing, and the second chain is decreasing. Let's also observe that each subcategory in this chain can be recovered from one of them, from D less than or equal to 0, by means of the shift functor. And the same is true for the second one. So we have the following obvious relation. So now the pair of these subcategories is called the standard T structure on the derived category on D of A. And now let's now look at some basic properties of this pair of subcategories. Well, the first property. Oh, sorry, just a moment. Oh, I'm sorry. Let's continue. So here are some basic properties of the standard T structure. The first property is obvious. We have already mentioned this a minute ago. The second property is that once we have a complex X concentrated, well, cohomologically concentrated in degrees less than or equal to 0, and the second complex is cohomologically concentrated in degrees greater than or equal to 1, then the only morphism from X to Y is 0. This is not entirely obvious, but, well, this can be proved somehow. Basically, the idea is that once we have a morphism from X to Y, it's obvious that it induces 0 in cohomology. That's the main point. Okay, and the third property is that once we have an object X in D, there exists a distinguished triangle of the following form, where X0 is concentrated in degrees less than or equal to 0, and X1 is concentrated in degrees greater than or equal to 1. Well, actually, I'd like to show you a sketch of proof of T3, not because this proof is important for me, but because this proof involves another important notion, namely the notion of truncation functors. So the idea is as follows. For each co-chain complex X, we can consider the following two truncated complexes. The first one looks like this. So it is concentrated in degrees less than or equal to n. So we have zeros to the right of the nth term. And in the nth term, we have the kernel of Dn. This is the left truncation of X. And the right truncation looks as follows. It is 0 to the left of the nth degree. And in degree n, we have the co-kernel of the differential Dn minus 1. The basic property of these truncations are that the left truncation complex, the left truncated complex, the cohomology of the left truncated complex is the same as the cohomology of X in degrees less than or equal to n, but it is 0 if I is bigger than n. And similarly for the right truncation. So it has the same cohomology as X at degrees greater than or equal to n, but the cohomology is 0 in degrees less than n. Now, let's observe that we have the following obvious exact sequence of co-chain complexes. So the left truncation is obviously embedded into X, and we have a natural projection of X onto the right truncation. And the resulting sequence is exact at every degree. And now to construct the distinguished triangle, so let's recall that what we want to do is to construct such triangle. Now, to make this sequence into a distinguished triangle, we use the following standard fact that once we have a short sequence of co-chain complexes, which is exact at every degree, then such a sequence fits into a distinguished triangle of the following form: a distinguished triangle in the derived category. So this is F, this is G, and this arrow, well, this arrow is not a co-chain map. It's a new morphism in the derived category, so it involves inverting quasi-isomorphisms. Okay, so if we now use this fact, we can embed this short exact sequence into a distinguished triangle. And we see that the axiom T3 is satisfied. So we have constructed the standard T structure on the derived category of an abelian category. Once again, I'd like to stress that here it was essential that A was abelian. Now let's introduce the general definition of a T structure. So suppose that A is a right exact category. Let's denote by D the derived category of A. And suppose that we have a pair of full subcategories of D. For each integer k, we can consider the respective shifts, the respective translations of these subcategories. So for each integer k, we get two subcategories, this one and this one. And we say that this pair T, this pair of subcategories, is a T structure on the derived category if the above properties T1, T2, and T3 are satisfied. So let's look at them once again. So this is T1, T2, and T3. Okay. Well, we have already an example of T structure, namely the standard T structure on the derived category of an abelian category. And the next example, example 2, is very important for us. This is the so-called right T structure on the derived category of a right quasi-abelian category. So this example generalizes example 1 to the right quasi-abelian case. This T structure was constructed by Jean-Pierre Schneiders in 1999. Or more exactly, Schneiders considered only case where A is quasi-abelian, it is two-sided quasi-abelian. And he constructed two canonical T structures on D of A, the left T structure and the right T structure. But if A is not quasi-abelian, but it is right quasi-abelian, it turns out that only one of them survives. But actually, we need only one of them. We need the right T structure. So to define the right T structure on D of A, we need a notion of a strict morphism. Suppose that F is a morphism in our category A. Then we can look at the following diagram. We can consider the so-called canonical decomposition of F. So the induced map, the induced morphism F bar, acts from the co-image of F to the image of F. And by definition, F is strict if this induced map F bar is an isomorphism. Here are some concrete examples of this notion. First of all, if the category A is abelian, then all morphisms in A are strict. And in fact, this property characterizes abelian category. If A is the category of Banach spaces or the category of Fréchet spaces, then it's rather easy to show that a morphism F is strict if and only if its range of X is closed in Y. This easily follows from the open mapping theorem. And in the case of the category of complete locally convex spaces, it turns out that a morphism F is strict if and only if F is an open map of X onto its range, onto F of X. Now, if we have a short sequence, so we come back to the general case of a right quasi-abelian category. So a short sequence of the following form in our category is said to be strictly co-exact at Y if the image of F is equal to the kernel of G, or more exactly, the canonical morphism from the image of F to the kernel of G is an isomorphism, and second, if G is strict. So in this case, we say that our sequence is strictly co-exact at Y. Let me make a short remark about the dual situation. We can also define strictly exact sequences. So in the case of strictly exact sequences, we require, again, this isomorphism, and also require that F is strict. Not G, but F is strict. As was proved by Schneiders, if our category A is quasi-abelian, and if we have a short sequence of the following form, then the sequence is strictly exact in all terms, that is strictly exact at X, Y, and Z, even only if it is strictly co-exact at the same terms. And this happens even only if the sequence is strictly exact in the sense of our previous definition, that is, in the sense that F is the kernel of G and G is the co-kernel of F. Okay, now we are ready to construct the right T-structure on the derived category of A. So as before, we assume that A is a right quasi-abelian category. We denote by D the derived category of A. And for each integer k, we consider the full subcategory of D, which consists of those co-chain complexes which are strictly co-exact at degrees greater than k. And similarly, we define the subcategory of those complexes which are strictly co-exact at degrees less than k. As was proved by Schneiders, the resulting pair of subcategories is indeed a T-structure on DOA. And it's obvious from the above definitions that if A is abelian, then the above T-structure is identical to the standard T-structure. Simply because strictly co-exact, in the abelian case, strictly co-exact, it means just exact. So this example generalizes, this construction generalizes the standard T-structure on the derived category of an abelian category. Okay, some more definitions. What we want to do next is to define truncation functors in the context of an arbitrary T-structure. So we have already defined truncation functors for the standard structure, which comes from an abelian category. Now we want to define truncation functors in the general case. So we start with an arbitrary T-structure. Arbitrary means, well, defined axiomatically. Here I don't assume that this T-structure comes from a right exact. I don't assume that this is the T-structure constructed by Schneiders. So we start with an arbitrary T-structure. We take any integer k, and we consider the inclusions of the respective subcategories into D. Oh, sorry. Yeah, that's correct. We consider this inclusion. And we can also consider the potential projection of D onto the category of complexes concentrated, well, kind of complexes concentrated in degrees greater than or equal to k. Formally, this subcategory can be more or less arbitrary. So since we work with an arbitrary T-structure, Well, what I wanted to say that if we work with the right structure, then this subcategory consists of complexes which are strictly co-exact at degrees less than k. Okay, so this, a standard fact is that this inclusion has a right adjoint, which acts from D to this subcategory. And the second fact is that this projection has a left adjoint functor. And these two functors are called the truncation functors. In the case where our category A is abelian, and the T structure T is the standard T structure, these truncation functors are identical to the truncation functors which were discussed before. So let's look at them once again. So here's the definition. So these are the truncation functors in the case of the standard T structure on the derived category of an abelian category. Now we define the heart. Again, we work with an arbitrary T structure, and we define the heart of T to be the intersection of the following two subcategories. In Russian, heart is serдцевина. A fundamental fact, probably the most fundamental fact in the theory of T structures, is that the heart of any T structure is abelian. This is not obvious at all, and this is a rather involved theorem. So the heart is always abelian. Well, here's a simple example. Again, if you take the standard T structure, which is defined on the derived category of an abelian category, then it is more or less immediate from the definition that the heart is equivalent to the original category A. So in this case, we get nothing new. Okay, let's now come back to the abstract setting. Again, we take an arbitrary T structure. And for each integer n, we define the nth cohomology functor relative to the T structure T as follows. We take an arbitrary co-chain complex. We shift it by n to the left, so that the nth term moves to the position 0. And then we apply the right truncation and the left truncation functors. Or currently, we can apply them in the opposite order for the simple reason that they commute. So what we get is a functor from the derived category to the heart of our T structure. And it is called the nth cohomology functor. Again, if we look at the simplest example where A is abelian and T is the standard T structure, we see that this cohomology functor relative to T is nothing but the usual cohomology, which makes sense for any abelian category. And now let's look at our main example. So we suppose that A is right quasi-abelian, and T is the right T structure constructed by Schneiders. In this case, the truncation functors look similar, but not exactly as in the abelian case. If we compare this with the abelian case, we see that the right truncation is exactly the same. So it is concentrated in degrees greater than or equal to n, and it has the co-kernel of dn minus 1 in degree n. But the left truncation is slightly different. Let's observe that the left truncation is concentrated in degrees less than or equal to n plus 1. So we have xn at degree n, and the image of dn at degree n plus 1. So this is different from the abelian case, because in the abelian case, the left truncation is concentrated in degrees less than or equal to n. What can you say about the respective cohomology functor? Well, if X is a co-chain complex, then the cohomology functor takes X to the following short complex consisting of two terms. So specifically, we have the co-kernel of dn minus 1 at degree 0 and the image of n at degree 1. In a special case, again, in a special case where A is abelian, this complex can be truncated further. It's easy to see that it is quasi-isomorphic to the kernel of this map. To the kernel of this map, which is, by the way, which is an epimorphism. And the kernel of this epimorphism is nothing but the nth classical cohomology. So this is true for an abelian category, but this is not true for an arbitrary right quasi-abelian category. So the objects of the heart, so the object of the heart of our T structure are not objects of the original category A. They are complexes of the following form. So these complexes are concentrated in degrees at degrees 0 and 1. And the only non-trivial error here, sigma, is an epimorphism. I'll not explain, I'll not define the morphisms in the heart in detail. Roughly, the morphisms of the category H are, again, equivalence classes of certain fractions. So again, this is a localization of a suitable localization of the category of all such two-term complexes. Okay, so now I come into an end of my talk. Now we can define the new Tor functor. So we fix an admissible subcategory of the category of all complete locally convex spaces. Suppose that A is a topological algebra whose underlying space belongs to C. And we consider the projective tensor product functor, or more exactly, projective tensor product bifunctor, which acts from the product of the category of right topological modules and the left topological modules to the category of complete locally convex spaces. So let's recall that before we consider this functor with values in the category of vector spaces and in the category of all locally convex spaces. But now it will be convenient to consider it as a functor to complete locally convex spaces. This is quite essential. So we now consider the total left-derived functors, which acts between the respective derived categories D minus. And since the category of complete locally convex spaces is right exact, we may consider the canonical right T structure on this category. We now define the new Tor functor as follows. We take a right topological module X, a left topological module Y in our category. We form their total tensor product, total derived tensor product, which sits in here in the derived category of complete locally convex spaces. And we compose it with the minus nth cohomology taken with respect to to our right T structure. So now we see that this new Tor functor is no longer a vector space, and it is no longer a locally convex space. It is an object of the heart of our T structure. So formally, it is a complex. It is a two-term complex of the following form. So by using this functor, we can give the following characterization of flatness. So if F is a left topological A module, then the following conditions are equivalent. Condition 1, F is flat. Condition 2, the projective tensor product with F, the projective tensor product functor, takes admissible monomorphisms to topologically injective operators. So this picture, so far the picture is exactly as in the case of flat Banach modules. Condition 3, for each right topological A module X, the canonical morphism from the total derived projective tensor product to the usual projective tensor product is an isomorphism in the respective derived category. And condition 4 says that for each right topological A module X, the functor Tor1, I mean the new functor Tor1, vanishes. And finally, this is equivalent to say that Tor_n vanishes in all degrees greater than or equal to 1. So this theorem gives us a characterization of flatness in terms of the new Tor functor. So I hope
again, harmony is restored. Can I say?
Restored in which sense restored?
No, harmony that was in Banach
Well,
space.
well, not
Pure
exactly.
algebraic. Now again we have.
Well, maybe. Well, not exactly, because again, of course, this new Tor is much more complicated object than the
Oh, well.
classical Tor, but nevertheless, well, here we are. So, nevertheless, I hope that this theorem is already, well, it already shows that the new Tor functor can be helpful sometimes, and also I hope that the new Tor functor can also be helpful in some other questions. For example, it can be helpful in studying the notion of weak homological dimension. But this is still a work in progress. And that's all I wanted to say. Thank you.
So thank you very much. So let's do this. Yes. So no brief questions now and brief comments.
I have a question.
Now,
Are there exist a computer file copy of this presentation?
Well, I can send you. Well, actually, I'm going to put it on the web page of the seminar.
Okay.
Well,
other brief questions
uh-huh.
and brief comments.
I have a question.
Do you have another one?
Ah.
Ext, something like that?
Yeah.
Ext, well, probably yes. I didn't try to define Ext in this way because so far, for my purposes, the classical Ext works well. But anyway,
I see.
well, we can try to do the same trick with the Ext functor and to see what happens. That would be interesting. Well, thank you for the question.
Thanks.
Okay. Now, so let us thank again to our speaker for very interesting things and excellent presentation. Yes, on behalf of both organizers, we thank you. And the next, our meeting will be the last in this semester. It will be Professor Anton Yurievich Savin from the University of Friendship of People. There is such a university in Moscow. Yes, and again, I say that it will be our next and last meeting. So thank to all people who are present, and we shall meet each other after a week.
I think that, Sasha,
Yeah.
I think that Norbert wanted to ask something.
Ah, Norbert, and why you were silent? Where is he?
Because I have the same question as Anar.
Ah, yes, okay. Okay, guys. So bye, and to our next meeting. Bye.
Okay.